Hi everyone, I'm Mingda Qiao from Stanford. I'll tell about a joint work with Guy Blanc from Stanford, Jane Lan from MIT, and Liang Tan from Stanford about properly learning decision trees in almost polynomial time. The focus of our work is a problem of turning black boxes into decision trees. Suppose we have some unknown function f that maps n input bits into a single Boolean output, and we have query access to f, meaning that we can choose an input x and get the function value at x. Our goal is to output some decision tree representation of f, meaning that we output some decision tree that is close to f. To motivate this problem a little bit, let me tell a few things about decision trees. First, they are very fast to evaluate. Suppose we have a decision tree of depth k, we only need to query k bits to get the function value, whereas the number of parameters in the tree could be exponential in k. Furthermore, decision trees are very easy to interpret it and explain its behavior because on a given input, it's very easy to understand which variables contribute to the decision of the tree. So decision trees are both simple and effective and well used in practice. Now back to our problem. We want our algorithm which transforms this black box f into a decision tree to be both fast and accurate. Here we measure the accuracy based on the fraction of inputs on which the tree T differs from the original function f. More concretely, we consider drawing this input x uniformly from the hypercube, and we want the probability that the two functions disagree to be bounded by some epsilon. For this problem to be possible to solve, we need some assumption about f, and we make the arguably minimal assumption that f indeed has a representation of decision tree with a small size. More concretely, we assume that this function f can be represented by a decision tree of size s, and then our algorithm should output a decision tree t that has also size s, such that the two functions are epsilon close to each other. Our main result is such an algorithm that runs in time polynomial in n, where n is the number of variables, and almost polynomial in s, the size of the tree. The dependence on s is s to the power of order log s. And furthermore, instead of assuming that our function f is exactly a size as decision tree, our algorithm still works even if f is only guaranteed to be close to a size as decision tree. So let's suppose among all the size as trees, the closest one to f is at distance opt. Then our algorithm is guaranteed to output something that is opt plus epsilon close to f. Another way to view this result is that our algorithm is somewhat robust to the noises, meaning that suppose this black box is a size as decision tree at the very beginning, but some unexpected noises corrupt a small fraction of the outputs. Even in the noisy case, our algorithm will output something nice. So here's a formal statement of our results. We use query access to this function f with n input bits, and assuming that f is opt as close to a decision tree of size s, our algorithm will run in time almost quadratic in n and almost polynomial in s over epsilon. And the output is a size s decision tree whose distance to f is at most opt s plus epsilon. So in learning theoretic terms, our algorithm is a learning algorithm for decision trees using queries. And our learning is both proper, meaning that our output is a decision tree itself, but not something more complicated. And our learning is agnostic, meaning that we don't require the ground truth f to be inside the class of decision trees. And one caveat or weakness of our result is that we only vote for the uniform distribution, and learning for general distributions can be much harder. To compare our work to previous results, we look at the parameter regime where the size of the tree is polynomial in n. In that case, our runtime can be reduced to n to the order log n. And prior to our work, the fastest runtime in this regime was n to the order log n. And this holds even for the realizable setting where the function is a decision tree of size s. And in fact, this is a very well-studied problem, and there have been at least three different algorithms achieving this n to the log n runtime. And they were due to Aaron Foy Hausler in 1989, Meta Radovan in 02, and very recently, due to my three co-authors, Blanc, Lange, and Tan in 2020. And in fact, the analysis for all three algorithms are tight, meaning that there are concrete instances on which the algorithms have to run in time n to the omega log n to achieve, to find an accurate tree. So in other words, to achieve our faster runtime, our algorithm should be a bit different from all previous algorithms. Now, let's get to the high-level picture of our algorithm. There have been two quite different approaches to learning decision trees in the literature. The earlier two algorithms fall in this bottom-up approach, and they are very similar to dynamic programming approaches that splits the problem into a few subtasks and solve those subtasks optimally, and then combine them into the final solution, the final decision tree. And in contrast, the recent algorithm of Blanc, Lange, and Tan uses this top-down approach that first determines the root of the tree, and then the two children of that root, and then all the levels one by one. I'll get into more details of this top-down approach later. But at a high level, our work draws ideas from both sides, from both approaches, and our final algorithm can be viewed as a combination of the BLT algorithm and the MR algorithm. Now let's look at the top-down approach to learning decision trees. This algorithm is essentially a greedy algorithm. So as a first step, we choose a good variable in some sense. We choose this good variable xi and put it as a root. And then the problem becomes the learning for two different subtrees. And that's essentially the learning problem for the restriction of f to xi being 0 or 1. So we can solve those two problems recursively. In other words, we put this good variable xi as a root, and then put the good variable for the two restrictions as its children, and do this one by one. And the crux of the design of such a top-down algorithm boils down to find a good definition of goodness of variables. And that's called the splitting criterion of the algorithm. So intuitively, we want this xi to be somewhat important or informative in the sense that knowing the value of xi gives us a lot of information about the function value fx. The specific criterion used by BLT algorithm is the influence of the variable, which is a useful concept from analysis of Boolean functions. So it's defined as follows. The influence of variable xi on function f is a probability when we draw a uniformly random input x that flipping the I split of x will change the function value. So that's intuitively how much influence this xi could exert on this function value. So to put things together, the BLT's top-down algorithm is as follows. As a first step, we find the variable xi that has the largest influence for function f. And this can be easily done using queries to f. We put xi as a root and solve the two subtrees recursively. And as a technical note, this algorithm will terminate once the tree reaches some pre-specified depth d. At that point, we'll label the leaves based on the majority votes. So as we have seen, this BLT algorithm is a greedy algorithm. So the crux of their analysis is that choosing the most influential variable as a root is a somewhat good choice. The main idea of this work is that we should be less greedy. So instead of looking at the most influential variable, we look at the k most influential variables. And we want to argue that among these k choices, there's an even better choice for the root. So let me get into more details of this difference. In the rest of the talk, we will focus on the realizable setting, where the function f is a size S decision tree exactly. And in this case, the main theorem in BLT says the following. Suppose we always choose the most influential variable as a root and do this recursively. And once we grow the tree to depth log s squared, that tree will be accurate for function f. In contrast, we prove a different theorem, which we call the less greedy theorem, saying the following. Suppose we look at the polylog s most influential variables at each step. Among them, there has to be a good choice in the following sense, that if we grow the tree up to depth log s, that tree will be accurate enough. So there's a trade-off between the number of variables we look at and the depth of the tree. So pictorially, the BLT algorithm will always choose the most influential variable and do this deterministically. So only one possibility is explored. In contrast, we consider a number of different candidates for the root, and we try all the possibilities to find the best tree. Now let's get to the details of the algorithm, the pseudocode of our procedure, which we call the less greedy procedure. It has query access to this function f, and we have a specified greediness parameter k that determines how many variables or how many choices we have at each step. We also have this depth budget d, so we'll only grow a tree up to depth d. If the budget is 0, we have to find a constant function, so it's just a majority vote. Otherwise, in the more interesting case that d is greater than 0, we find the k most influential variables of f, and we call that set S. For every variable I in S, we will build a tree with xi as a root, and the two subtrees are obtained by recursively call this less greedy procedure on the two restrictions of f, and we call this tree Ti. Among all possible Ti's, we choose a tree that has the smallest distance to f. So that's basically our procedure. So what's the time complexity of this procedure? It's a recursion of at most depth d, and the branching factor is 2k because there are k choices, and we need to solve the two subtrees for each choice. So the total number of recursive calls is 2k to the power of d roughly. And the overhead in each recursive call is reasonable. It can be implemented in poly n time. So in the end, the runtime will be poly n times this 2k to the d term. To analyze this less greedy algorithm, it is useful to understand the search space of this procedure. So in other words, what are the trees that could be built by this less greedy algorithm? So we can see there are two properties of such a tree. First, the tree must have depths at most d, and that's determined by the depth budget. And second, more interestingly, for every node in that tree, let's suppose that node queries variable xi, that xi must be among the k most influential variables for the restricted function f pi, where pi is the path from the root of the tree to that internal node. So in other words, the tree that could be built by a less greedy algorithm is both shallow and satisfying that every internal node queries an influential variable. Recall that we have this less greedy theorem, which we claim that we will prove. And I claim that assuming this theorem, we are done. So recall that this theorem says the following. Suppose we consider the poly log S most influential variables at each step, and we build the tree up to depth log S, we will find an accurate tree for the function. So this essentially says the following. If we call less greedy procedure with k and d chosen as follows, the output of less greedy will be an accurate tree for f. And we can compute the runtime of this algorithm. It's the number of recursive calls will be s to the power of log s. So the runtime will be poly n times almost polynomial s as we wanted. So in the rest of the talk, I will focus on the proof of this less greedy algorithm, less greedy theorem. We prove the theorem using a pruning procedure. So it's a really constructive and algorithmic proof. So we start with this decision tree representation for f, which has size s. Our pruning procedure will output some pruned tree, which we call t prime. And this pruning procedure satisfies the following three conditions. The first, this pruning procedure doesn't introduce much error, so the distance between t and t prime will be less than epsilon. Second, the pruned tree t prime is shallow. It has depth d at most log s. And third, more importantly, it satisfies that every internal node queries an influential variable. Here we note that we use a slightly different criteria of influential. We require the influence of xi to be greater than some tau, chosen as a function of epsilon and s. And in fact, it's an easy fact that there are at most k different variables with such a high influence for any internal node. So in fact, this third condition is stronger than what we said before. Assuming this pruning procedure exists, we already proved the less greedy theorem because Condition 1 says that T prime is an accurate tree for T, and conditions 2 and 3 together implies that this T prime is inside the search space of less greedy. So less greedy will find a tree that is at least as good as T prime. Now let's step to the pruning procedure. It has 2 steps. In the first step, we guarantee that the tree T prime has a small depth. And this is easy because it's a standard fact that if we truncate the decision tree at level log S over epsilon, we will only incur an error of epsilon. So this is the easiest step. And the harder step is to ensure that every node queries an influential variable. We will ensure this property level by level. So we start with the root. Let's say the root queries variable xi. Then we ask, does xi have an influence of at least tau? If so, xi is a good root, and we can proceed with the 2 subtrees recursively. Otherwise, if xi doesn't have a high influence, by definition of influence, we know that the 2 subtrees in this tree must be close to each other. And in particular, at least one tree must be close to the function f. And we can keep that closer subtree and discard everything else. So we discard both the root and the subtree that is farther from f. And we will keep the closer subtree and focus on pruning that tree. And this can be also done recursively. So in the end, this pruning procedure is a recursive procedure, and we can analyze it inductively. Now we're ready to put everything together. We have this 2-step pruning procedure that first ensures that the tree is shallow, and then ensure that every internal node queries an influential variable. In the end, the pruned tree will be inside the search space of less greedy. So if we call less greedy with appropriate K and D, we will find a tree that is at least as good as the pruned tree, which means that we will find one within epsilon distance to the original function. And the runtime of less greedy, as we said before, is polynomial in N and roughly polynomial in S. It still says S to the power of log S. So to recap, our main result is a proper learning algorithm for decision trees that runs in time polynomial in N and almost polynomial in S. And one immediate open question is to improve this runtime to fully polynomial. And it seems a challenging problem even for the realizable setting where the function is a decision tree. And one possible avenue towards such a result would be finding some more sophisticated splitting criterion beyond the notion of influence. And we can imagine there could be some structural results similar to our pruning procedure that could further reduce the search space of decision trees and facilitate this polynomial runtime. Thank you all for listening.